Okay, so I'm gonna give a presentation on cryptography in Ethereum. Let me check the thing. Yeah, this could be a little bit better. That's better. Okay, so let's get started. So the presentation is actually on GitHub. You can access it by, well, it's on the internet and on GitHub. dtimel.github.io/presentations, and then you just click on cryptography. So the outline of this presentation is going to be, first we're going to talk about RSA and give one example of where it can be used, which is encryption. By the way, on a more meta level, so cryptography, cryptosystems can be used for three things, among others. Number one is encryption, number two is key exchange, and number three is digital signatures. Next, we're going to kind of improve our setup by discussing the discrete log problem, and we're going to apply that to talk about the Diffie-Hellman key exchange, which has been used in the internet for decades and is still used today. And finally, we're going to improve on both of these systems by talking about elliptic curve cryptography. And in particular, the elliptic curve digital signature algorithm. So once we do that, we'll have covered all three of the major use cases for crypto system. That's encryption, key exchange, and digital signatures. And in particular, we'll talk about one specific elliptic curve called SEC256K1, which is the curve used in Bitcoin and Ethereum. And finally, we'll talk about elliptic curve cryptography in Ethereum. So let's do it. So let's back up a little and talk about the intuition behind public key cryptography. So initially, there was no public key cryptography. In symmetric cryptography, both the sender and receiver must have the same key. Now, that poses huge limitations to your crypto system, because that means that in order to be able to communicate, you need to have a secret key. So you need to, before that, communicate some kind of shared secret password. Can we do better than this? So we can separate this into two processes, decryption and encryption. Now, decryption, obviously that has to be private, because if it was public, it wouldn't be cryptography. So then we look at encryption. By the way, so the intuition behind this slide is we don't want to have a shared key. So actually there should be three possibilities for each, but ruling out the shared key part. So now we just have two possible options, which is public or private, because anything can either be public, private, or shared. So decryption definitely has to be private. And then for encryption, well, it can't be private because then you could only encrypt stuff for yourself. So let's make it public. And basically, like, this kind of categorization of these two things is the intuition behind asymmetric or public key cryptography. The reason it's called asymmetric is there are two keys, one for encrypting and one for decrypting. So to understand how public key cryptography works, let's talk about this concept of a one-way function. So one-way function is a function that's easy to compute in one direction, but very hard to compute in the opposite direction. So this generalizes some very different concepts in computer science, such as hash functions and trapdoor functions. What's a trapdoor function? It's a function that's easy to compute in one direction, but very hard to compute in the opposite direction without special information. So in order to the way this connects with public key cryptography is the encryption will be the one-way function, and the decryption will be the opposite way with the knowledge of special information, i.e. the private key. So we need to find some trapdoor functions in order to do public key cryptography. So we're going to discuss three today. First one is factoring integers. Second one is the discrete log problem over finite prime fields. And the third one is the discrete log problem over elliptic curves. So the RSA system is quite simple, so let's just go through it very briefly. You pick two large primes, P and Q, 2,000-bit or 3,000-bit primes, so extremely large primes. Actually, it's not 2,000 and 3,000. It's the square root of those. So actually, 1,000 and 1,500. If you want to achieve a 2,000/3,000-bit level security. So I said that incorrectly, and so I corrected myself. Next, you compute the product of the two primes, and you compute the value of the Euler's totient function for those for that product. Finally, you choose any d between 1 and that value, and you choose e to be the multiplicative inverse of that number, mod phi n. Encryption is very simple. You take some message x, and you put it to a power of e. You obtain some value y, and you send that across the wire, or across mail, or whatever your transport communication layer is. Whereby e is the encryption key, i.e. the public key. Decryption is very simple as well. You take what you received, and you put it to the power of your private key, or d. If we put both sides to the power of d, we obtain x to the ed, which, by our assumption that ed is congruent to 1 mod phi n, therefore ed can be expressed as some multiple of phi of n plus 1. So that's what we do right here. We express ed as some multiple of phi of n plus 1. And now we need a lemma to prove that it's congruent to x mod n. And if we prove that, we'll prove the correctness of the crypto system. So let's do that. So in fact, we're going to prove a stronger statement. We're going to say that n can be a product of distinct primes. So not just the product of two distinct primes, but any number of distinct primes. And then we have this property. So I'm just going to outline the proof. It's very simple. We're going to prove it separately for each of the prime divisors of n. We're going to separate into two cases. Either p does not divide x. That's the simpler case. Then we just get directly x to the power of phi of p is congruent to 1 mod p by Euler's theorem in number theory. And then we can just put both sides to the power of h and multiply by x to get the desired congruence. Next case is when p does divide x. Then we get the congruence immediately because both sides are congruent to 0 mod p. So the reason these two are congruent to each other mod p is that they are actually both congruent to 0 mod p, because we are assuming that p divides x. So hence, this congruence is true for every single prime divisor of p, and by the Chinese remainder theorem, it is also true for a product of distinct primes n. So we just proved the correctness of the RSA crypto system. That tells us nothing about its security, but it's one step out of a million. So what are the possible attacks? So let's have a look at how we actually defined the two keys. So this is public and this is private. The decryption key is private. So if one were to able to find the multiplicative inverse of E mod phi of n, they will be able to find D. So what prevents them from doing that? The problem is finding phi of n. So why is phi of n so difficult to find? Because the reason that phi of n is so difficult to find is we don't know this product. And why do we not know this product? Because we don't know P and Q. So this is very, very important, and this leads to the following attack vectors. So if you could factor n efficiently, then the whole thing, then from step 1 you could replicate the setup, and therefore you could find the private key. If you could find phi of n without factoring n, then you could also emulate the setup from step 3 and therefore find the private key. And finally, the last attack vector is even if you don't know phi of n, if you could find x, i.e. replicate the setup from the from step 4, whatever it was, then that would also be a problem. So these are the possible attack vectors on RSA. So let's look at the security level of RSA. So basically there's a bunch of algorithms that allow us to factor integers. The most efficient one of them is called the general number sieve or GNFS algorithm. And it actually runs, I wouldn't say efficiently, but yeah, the main point is that it allows us to factor integers in some way that reduces the security level of RSA. So this is a very interesting comparison between the security levels of RSA and of a very efficient symmetric key algorithm such as the advanced encryption scheme. And I think here they're assuming that AES has to be brute forced. So you can see that it requires much larger keys, which is not good. Can we do better than this? So let's look at another trapdoor function, the discrete log problem. So let G donut be a cyclic group. That's just what I'm going to call the operation donut, with n the order of the group. And let alpha be a primitive element, which is just a fancy way of saying a generator, and beta be an element of the group. Then the discrete log problem says find x such that alpha multiplied x times together is equal to beta. So alpha here is public, beta here is public, x is private. So let's try to figure out a cyclic group where this would actually lead to an effective crypto system. Let's try the most simple cyclic group, ZP plus, which is just the cyclic group of modulo residues of a number p with respect to addition modulo p. Then we have alpha times x is equal to beta mod p, because if the operation is addition, then if we perform addition x times, then we obtain x times alpha. So the attack would then be find x prime such that alpha times x prime is, so then the problem is alpha times x is congruent to beta mod p, and how can we solve that? Well, here's a possible attack. What if we find x prime such that a times x prime is congruent to 1 mod p? That would be a big problem, right? Because then we could just set x to be equal to beta x prime, and here we multiply both sides by beta, then we plug in x, and we obtain this. So that would break the entire problem. Now, what's the time complexity of this operations? So, unfortunately, both of these can actually be solved in quadratic time with respect to the size in bits of p. Not good, because what does it involve? It essentially involves just finding the multiplicative inverse and then multiplication modulo p. Multiplication modulo p can, on the hardware level, be done in O of 1. It's a built-in operation, and multiplicative inverse is actually a quasi-linear problem. So it actually runs even slower, or I should say even smaller than quadratic time. Okay, can we do better? How about ZP star times? What's ZP star times? It's the cyclic group you get by filtering out everything that is. Okay, so when p is prime, it's a simple definition. It's the group of 1 through p minus 1, where the operation is multiplication modulo p. So if we're performing multiplication x times, we get a to the x. So the discrete log problem becomes a to the x is congruent to beta mod p. For example, find x such that a to the x is congruent to 5 mod 19. That's an example. Does it? Well, yes. I mean, you're right. Yeah. Well, it does. So, like, logarithm in some abstract sense is just finding the number of times you have to do an operation to get some number, right? When applied to the real numbers, it's the amount of multiplications you have to do. When applied in this case, it's also the amount of multiplications. When applied in the previous case, it's the amount of additions. Totally agree. This is much more similar to the regular use of the word log than the previous case. Great. So we've just found a discrete log problem that actually is not that easy to solve, which is exactly what we wanted. So now we're going to apply it to build a crypto system called the Diffie-Hellman key exchange. Diffie-Hellman key exchange goes as follows. P and alpha will be public parameters. Alice and A will choose their private parameters A and B. Alice computes alpha to the A, mod P. Bob computes alpha to the B, mod P. And then they exchange it, and they both put whatever they received to the power of their own key. So Alice will get alpha to the B to the A, and Bob will get alpha to the A to the B. In effect, both will get alpha to the AB, and hence they will both be able to establish the same key. So this is an algorithm family called key exchange, where you're able to exchange a secret key in a secure manner. Of course, it's a subset of public key encryption, but it's just a faster way of doing it because your browser, for example, can send the let's say this to the server, and the server can send the stuff back to you, and you can continue computing. So it only requires one back and forth communication between the two parties. Cool. So to summarize, the discrete log problem in ZP star or ZP multiplication in the multiplicative group is a hard problem. But unfortunately, there do exist attacks. So Unfortunately, I don't have the time to discuss them, but you can look them up by the names square multiply method, which is very simple, but index calculus, which is very, very cool. So, where does that leave our crypto system? Well, it turns the advanced encryption scheme. So it's just a modern symmetric encryption scheme. So where does that leave our current crypto system? Well, it turns out actually we didn't improve at all. So due to the index calculus method, which is a super effective method for breaking the discrete log problem, we actually didn't improve. By the way, there is not some kind of magical relationship between these numbers. It comes from empirical evidence. So a lot of these are kind of rounded. So this might, you might run a benchmark and it will tell you that this is 86 and this is 1,000 and this is 1,010. And then you kind of, compare at the same bit level, you put them together. So this comes from empirical benchmarking evidence rather than theoretical computer science. The reason that the discrete log problem is easy to break, is that there exists a homomorphism between the set of integers and the set of integers mod p. And it's really this homomorphism that allows us to first sort of solve the, basically use information from the set of integers to break the discrete log problem in ZP. So that's the problem. And the solution to that would be to look for a cyclic group that does not have this homomorphism to its supergroup, superset. So an example of that would be elliptic curves. So let's have a look at elliptic curve cryptography. An elliptic curve is a curve defined by the equation y squared is equal to x cubed plus ax plus b, where the curve is non-singular, i.e., in basic terms, I believe this means that if you take the sort of the cubic equation in x, then the discriminant is not zero. Graphically means that there are no sort of weird points that are not smooth, i.e. not differentiable. And using this curve over the real numbers for now, if we define an additional point called the point at infinity, which we're going to denote with the infinity symbol, then we actually get an infinite group. And the group operation, which is called point addition, is going to be the reflection of the x-axis of the intersection of the line between 2 points and the curve. So I believe I have a GIF that explains that. So let's have a look if it's here. So this is a plus b, now a plus c, and now a plus d. Bam. Let's watch it again. A plus b, a plus c, and a plus d gives us e. Yeah, so it's the group operation is the reflection in the x-axis of the intersection of the line between the 2 points and the third intersection point. So we write the line between those 2 points, we find the third intersection point, and we reflect it in the x-axis. Same here, and same here. So this GIF, I just found it on the internet. We could describe it as a plus b plus a plus a. But since the group operation is associative, we could just label it as 3a plus b. So this right here is the result of doing this point times 3 plus this point times 1. Cool. So elliptic curves, just a little bit real-world stuff. They got a lot of attention in modern mathematics. They actually can be also used to factor integers, funnily enough. And they were, for example, used by Professor Wiles to prove Fermat's last theorem in 1993. But they're also used in crypto. So let's have a look at that. So in cryptography, we're going to define an elliptic curve to be a set of points, integer points, obviously, satisfying the same equation over a finite field, usually a set of numbers modulo a prime number, i.e. the modular residues of a prime number, together with, again, the point at infinity. And we're going to use the same formulas as elliptic curves over real numbers. So far, all this elliptic curves operations we saw, there was the geometric intuition behind it. Turns out all of that can be done algebraically as well, and that's what computers use. And we're going to just take those formulas. They're not that difficult. They're actually very easy. It's like high school algebra. I just don't have time to put it in here. We're going to take the same formulas, and we're going to apply them to elliptic curves over finite fields. Reason we do that is if we take it over a prime p, we lose the geometric representation. So let's have a look at an example. So this is the elliptic curve. Y squared is congruent to x cubed plus 2x plus 2 mod 17. So I actually hand wrote all those points in an online calculator. And you can see it looks nothing like an actual elliptic curve. But yeah, so pretty sure that those points are spread out kind of randomly. There's no relationship except the obvious symmetry across the line. Y is equal to 6.5. Oh, sorry. Y is equal to 6, 7, 8, 9. Y is equal to 7.5. Just this line right here. Yeah, 6, 7, 8.5. Yeah, so apart from that, I don't see any other fancy relationships going on here. By the way, just a side note, how could we actually find those points? We would find them, well, there are multiple ways. One would be to actually try to, brute force this. That's very inefficient. Another would be to take a generator, a primitive element, such as this one. Actually, on this specific curve, every single element is a generator, but that's not generally the case. So we could take any point here and just keep putting it to higher powers and powers. By powers, I mean first adding it with itself, then adding the result to itself, then adding that result, and keep on using point multiplication, or I should say point addition, to arrive at all the points on the function. Any questions so far? So what was I going to say? Oh yeah, why are they all actually generators? The reason is, turns out the order of this group is 19. As you could probably count, there are 19 elements. Well, I said that incorrectly. There are 18 elements on the image, but then there's also the point at infinity. So in all, there's 19 elements. And Lagrange's theorem tells us that the order of any subgroup will always divide the order of the group. And also, it also tells us that any element will generate a subgroup. So in other words, if we take any element and we start adding it with itself, i.e. start doing point multiplication, then it will generate a group, and the order of that group has to divide the order of the actual supergroup, which is 19. So since 19 is a prime number, the only way that's possible is if the order of the subgroup is 19 as well, i.e. every single point here will generate the entire group, except for the only point that has an order of 1, which is the point at infinity in this case. Make sense? So this is just some like abstract math that I'm trying to like put across to apply it to elliptic curve cryptography. Basically, to summarize what I said, if you take any element in any group and you start adding it with itself, so doing group operation on itself, it will always generate a subgroup, a cyclic subgroup. And the order of that subgroup, i.e. the number of elements of that subgroup, always has to divide the number of elements of the actual group. Now, if the number of elements of the actual group is 19, we only have the options 1 and 19. Now, we know a group must contain an identity, so the only option for it to be 1 is if it's the identity itself, i.e. the point at infinity, and if it's not that, then it's got to be 19. So that's the justification. Now you might ask a cool question, which would be, what's the relationship between this and 19? You could ask, could there be 17 times 17 points on the curve? Like, could every single point here be covered with red? And the answer is no. So there was a guy called Hasse, and he actually proved that for elliptic curves, the order of the group is very, very similar to the prime number taken as a constant. And we'll see that in a while with the elliptic curve used in Ethereum. Okay, so for elliptic curves, we have a thing called domain parameters. So for this curve, by the way, this should say mod p. You guys can correctly read it. We clearly need P, A, and B. We also need G, which is going to be the generator. It's just any point on the curve that generates the entire group. And we also need N, which is the actual order of the group. And we're also going to define this new thing called cofactor, which is not really a parameter because it's actually computed from the other ones, but it's still cool, so we'll still include it in the bunch. And it's computed just by dividing the order of the group with n. Most of the time in cryptography, you want h to be 1 because higher h's, in theory, they reduce the security of your system. So unless you have a specific reason you want to have a cofactor larger than 1, such as an efficient implementation, some kind of efficient operations on specific curves, you want it to be 1. Reason is you want n to be as large as possible to increase the security of the system as much as possible. So in the case that we just discussed, we had 17, 2, 2, generator could be anything, 19, and h is equal to order of the group, which was 19, we said, divided by n, which was 19 as well. So this would be 1. N is the order of the group. Yes, that's right. That's exactly right. So n as well is uniquely defined by P, A, B, and G. Okay, so it turns out that if we use, large keys, 256-bit keys, and etc., computing n is actually quite difficult. So that's why there's this concept of named curves, which are standardized curves that are published that we often use for cryptography. However, there is a deep suspicion that the curves published by the NSA, for example, actually include backdoors. And I have some content about this. Let me just look it up real quick so you guys can take a 2-minute break. Okay, I found it. So these are just my speaker notes for the presentation, and here it is. And it filtered out the comments, so now I open them again, and I can find it. Okay. So, yes. So, for example, this standard called Dual ECDRBG, it was a NSA recommended cryptographic pseudo-random bit generator. It came under criticism in 2007 because constant recommended for use in the algorithm could have been selected in a way that would permit their author to predict future outputs given a sample of past generated values. In September, blah, 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 a former NSA contractor, Edward Snowden, suggested that the NSA generated one of the random number generators used in a 2006 standard containing a backdoor for the NSA. So that's like some colloquial evidence, right? Also, the P curve standardized by the NSA, the coefficients are chosen using really weird seeds, like BD713447999D5, etc. They're just completely random looking. Well, you know, that's the thing. They're not really random, right? So oftentimes when you want to prove that something is really random, you do something, you pick a sequence of numbers that is very natural. So for example, the first 100 digits of pi, or the first 100 digits of E or phi, right, of a constant. But if it's something that you know, has no justification, then it's quite suspicious. Or alternatively, if you also, you know, pick the 100 digits starting at the millionth digit of pi, that's quite suspicious as well, because pi contains any string of digits, if you look far enough. So that's pretty cool. And additionally, also, talking with some professional cryptographers myself, a lot of them, or one of them, my friend, he also believes that NSA inserts backdoors into its algorithm. So that's just my own colloquial evidence. So on a meta level, it turns out that elliptic curve discrete logarithm problem is isomorphic to discrete logarithm problem in the group that we already discussed. If it's isomorphic, why do we use elliptic curves? The short answer is isomorphisms don't capture computing costs. For a generic cyclic group, Pollard's row algorithm calculates the discrete log in root n. And we also have a proof that no faster algorithm exists for generic groups. But the problem is, there exist faster algorithms on specific groups. And as we saw above, currently, no faster algorithm exists to solve log on generic elliptic curves. But some elliptic curves have faster discrete log algorithms. Is there something that I wanted to say here? Right, so this links to the concept of a backdoor. So what is a backdoor? It's picking a curve where you know a more efficient way to solve the discrete log problem. So that's really what it means in cryptography to have a backdoor. Okay, let's summarize where we're at. So let's compare everything to symmetric key encryption. RSA, yeah, we can do crypto with it. Very large keys, extremely large keys. which probably also means very ineffective, but I'll get to that in a second. Discrete log, it looked pretty promising at first, but then we found out this homomorphism and like this index calculus method, so it actually turned out not to be any better. What's up? What do you mean? Oh, so this is the size of the key in bits versus the security of the system. So the number of operations needed to brute force it or to hack it in any way, in fact. Yeah? So the number of operations required to... No. So the way this works is it's in columns. So the equivalent of an AES crypto system that's 80-bit is an RSA crypto system that is 1024 bits. Yeah. No, so it's just the limitations of markdown tables that doesn't allow me to join the different columns, but this security level in bits applies to all three columns. No. So it's not like security level and bits. It's security level in bits of all three of these columns. Make sense? So this is security level in bits, this is security level in bits, and this is security level in bits. Because there's three different columns of numbers. But the title applies to every single column individually. Oh, so sorry about, I didn't realize that was confusing. I realize now that it is. So basically this says that the number of operations required to break an RSA problem with a key length of 1024 bits is the same, approximately, more or less, as the number of operations required to break an AES encryption of key length 80 bits. Okay? The same thing. So this just says that it's just comparing different key lengths. That's what it is. And cryptosystem. Sorry. It's not comparing different key lengths. It's comparing different cryptosystems. So this column says the number of operations required to break an RSA encryption with key length 3000 bits is the same as the amount of operations required to break an AES encryption of key length 160 bits. 128. Okay? Exactly. Security. Difficulty, security, number of operations. Exactly. Yeah. Well, that's the thing, it wouldn't, right? Because it's not a constant multiple. This is about 12 times more. This is about 16 times more. This is about 30 times more. Yeah, maybe. No, you guys are right. I copied this from a textbook, and the textbook had it exactly like this, but I guess it also had some explanation, which I didn't sufficiently provide. Cool. So now the reason I was going to show this table was to summarize where we're at. So right now, we just finished talking about elliptic curves. And it turns out that they're very efficient. So no algorithm exists that would, for well-chosen elliptic curves, no algorithm exists that would be better than Pollard's raw algorithm. So remember, I mentioned that Pollard's raw algorithm can solve discrete log for any cyclic group. So, and it can do it in root n. So if we choose our elliptic curve well, then we actually will end up with a curve where there doesn't exist an algorithm that is better than Pollard's for algorithm, right? So Pollard's for algorithm does it in root n. So for example, if we have 160-bit and we square that, then we get 80-bit security. So for any cyclic group, we will never be able to do better than 2x of these numbers. Never. And yeah, never. Because there is an actual algorithm that solves it for any cyclic group. So we'll never be able to do better than 2x times this number. And but also there exists a proof that this is the minimum bound. There isn't an algorithm that would what am I trying to say? Basically, there is a proof that there will never be an algorithm that is that can solve it better than 2x.
Within the domain of elliptic curves.
Sorry? Yeah, within the domain of elliptic curves, yeah. No, within any cyclic group.
Okay, so whatever way of the algorithm
Yes.
say,
Yes.
we can go lower than
Exactly. Exactly. Yeah.
or vice versa. If you go lower by
Yeah.
x,
Yeah.
means that we are always less secure.
Exactly. Exactly. So I should say that this applies for like well-chosen elliptic curves. So if you choose your elliptic curve badly, there might be an algorithm that solves it in a much more efficient way, right? That's called a backdoor, or badly chosen algorithm. But if you choose your elliptic curve well, then this is what you can do, right? And yeah, basically what I was trying to say is that we also have proofs that we'll never be able to go above this number, and we'll never be able to go below this number. We have proofs for both of these directions.
Sorry, so that would mean that if we would utilize more bits, that it would be less secure.
Sorry? If we what?
If we would utilize more bits within the elliptic curves, then it would be less secure.
More what? More bets?
More bits.
No. 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 What I said was that for a well-chosen elliptic curve, we know that this will never be larger than 2x of this, because Pollard's algorithm is able to solve it with a factor of 2x. This is to the power of 1/2, so that's a factor of 2. So we know that we'll never have to go above this number, or never be able to go above this number, because there exists an algorithm for that. But there's also proof that we'll never be able to go below this number, at least for cyclic groups in general. For the specific case of elliptic curves, there might be an algorithm that goes below, and for very specific elliptic curves, there might be an algorithm that goes even below that. But we want to choose our elliptic curves well so that they're secure, so that we don't go below this. Does that make sense? Watch the recording afterwards, and then maybe it will click or something like that. But yeah, like I'm trying to explain it as well as I can. Cool, let's continue. So what can we actually do with elliptic curves? The first part is we need to generate a key pair, a private and public key. So we're going to generate a private key called DA just by picking any random number among the possible numbers between 1 and the order of the group -1. And then we take the generator element and we add it to itself, DA times. Yeah, so that's basically private and public key generation in Bitcoin, Ethereum, basically any cryptocurrency out there. what can we do with an elliptic curve-based crypto system? That's what we're going to talk about next. One thing we can definitely do is digital signatures. ECDSA, elliptic curve digital signature algorithm. Let M be a message. Compute E to be the hash of M, and compute Z to get the most significant bits of E. By the way, this 5, I don't know why I put it there. It shouldn't be there. It's just whatever the constant is, probably 256. Pick K to be a random number, and compute K times G. Once you have that, the signature involves two numbers, R and S. R is going to be the x-coordinate of your point, and S is going to be, I don't have to read it out. It's going to be the inverse of the number you chose, multiplied with the hash of your message, and the x-coordinate times your private key. And you do everything mod n. And you send the message and your signature across the wire. Because I'm using x1 over here. But I could have just said that R is, let's call this point P, and I could have said it's like P dot x, like the x-coordinate of P. So this is signing. Let's have a look at verifying. Oh, even before we get to that, K must be chosen randomly. A lot of these crypto systems, the way they work is once you change one thing, the security of the whole thing diminishes. That's very, very often the case. For example, Sony used to sign PS3 games with a static N. I'm not sure if static here means they used it for all their games or if it means that they used it for just 2 games, which is often the case in crypto. It's enough to use something twice and the security is 0. And therefore, in 2010, a group called Fail Overflow published Sony's private key. Now let's have a look at verification. So verification works very similar to signing in the first 2 steps, but becomes different after that. Question: do we need to hash the message? Why do we have to do that? Why don't we just take the message itself, assuming that it's appropriate length, such as 32 bytes? Then we could get rid of this step. We could probably get rid of this step. We could just send the hash. It would make everything simpler for us. Well, the answer is we can't do that. Otherwise, our crypto system, the security breaks down. One of the security levels we want to have is called existential unforgeability. And it means that it's impossible to sign anything with that private key. To obtain a signature of anything that would correspond to some private key. And if we don't hash the message, it is possible to obtain a signature of something that wasn't actually signed. I don't know if I have a mathematical example of that. I don't, but you can start by reading this tweet by a Bitcoin core developer and professional cryptographer, and he tweets, elliptic curve digital signature algorithms where the message isn't a hash is insecure, because you can obtain a valid signature for any public key that you want simply by picking 2 random numbers A and B, computing some point, and then we can construct a valid signature for some message, random message, this. So this is the way that people have tried to claim that they're Satoshi, by essentially, taking Satoshi's public key, which is the public key of the first the first Bitcoin transactions, the Genesis block transactions, and essentially they've done this attack. So they picked A and B, and then they got this point, and then they got the signature. And if you check this using verification, it would say yes, this signature was signed by that private key, and then you would be able to obtain the message as well. But the reason for that is that we are not providing the pre-image of the message. So essentially, think about it in two ways. So you have this attack, and this attack can generate messages. But part of the protocol is that the message must get hashed. So the message that it generates, they should actually be hashes of some other messages. So if you think about it, this attack, you can generate some, a huge number of hashes to the 256, and then each of those hashes can generate, an infinite number of possible messages. So the reason, here's a fun fact. Think about it this way: if the hash function was broken and you could find a preimage for anything, then with this message or hash, we could actually find the actual message corresponding to this. So if the hash function was broken, we would actually be able to do existential forgery for the actual EDCSA algorithm, which we can't do because the hash function is assumed not to be broken. Okay, so in other words, ECDSA, for its security, assumes hash function is not broken. Otherwise, we could break existential forgery. Now, consider an even stronger attack. What if we were able to use this attack to compute any message? Well, then actually the hash function wouldn't even have to be broken. Why is that? Because we would just find, any message that we want, such as, Adam sending me 10 Bitcoins. Then I would hash it, and then I would be able to use this attack to figure out the signature for that hash. Essentially, that would break the entire ECDSA as we know it. So that would be very, very bad. Luckily, there doesn't exist an attack that allows us to find a signature for an arbitrary message. So this message is uniquely generated by picking the values A, B, and B, and that's why I say there's this, the attack generates these 2 to the 256 messages or hashes that then generate the infinite amount of messages. So there isn't a way to go from hash to attack. There's only a way to go from attack to hash. So this is luckily, for now, secure. So I don't know, I just thought about that this afternoon. I found that pretty cool. So let's go back to what we were talking about. Equivalently, if someone provides a signature on a hash but cannot provide the original message, it is not valid. Yeah, that follows from what I said. And there's even a script right now in Python that you could run right now on your computer that would allow you to prove that you are Satoshi, and it's obviously not correct. So lesson to learn here for you guys and for me is in ECDSA, you must hash the message in both signing and verification, and furthermore, what should be sent across the wire is not merely the message, not merely the hash, but the actual message. That's the only way that ECDSA is secure. Cool, so let's wrap up. Oh, we also have another cool thing. This is called public key recovery. So, by the way, I am not sure if Bitcoin uses this or not, because I literally found 2 conflicting answers on Stack Exchange, which tends to be a very, very reputable source of information. One of them saying that Bitcoin does use public key recovery. They're saying that it doesn't, and I'm not a Bitcoin expert at all, so maybe somebody could help me out with that. But in any case, Ethereum uses this. So let's talk about it real quick. So again, you compute Z, and let R be the set of points with X coordinate the same as in the signature, RS. Then the two possible public keys are, as given on the presentation. However, it turns out, oh yeah, and then you could, to prove correctness of this algorithm, you could take these two keys and you could plug them into the verification algorithm on the previous slide to prove that this verification algorithm is also correct. And then for the verification, you check that one of the keys that you found out actually corresponds to the actual public key. Now there's a small problem. R was computed modulo n. If n is smaller than p, then there is a very, very small chance that there could be, up to very many public keys corresponding to an R. For example, in SEC 256K1, there are up to 4 possible such keys. Now, I wish I had a whiteboard because then I could show you exactly why this is true graphically, but I don't. So we'll skip that. Now, this verification algorithm has been discovered very, very recently. I think in 2009. And it's actually, only 5% slower than regular ECDSA verification, which is super duper cool because we don't have to send across public keys if we omit the last part. So if we omit this last part, we don't actually have to send across the wire the public keys, and we don't have to store them. This doesn't compromise security at all, is only 5% slower on the CPU, and allows extreme savings in terms of bandwidth and storage. So this is what Vitalik Buterin chose when he was developing Ethereum. We talk about elliptic curves, cryptography, elliptic curve digital signature algorithm. We're getting more and more specific. SEC 256K1, the rock star, coming on stage right now. It comes from the standards for encryption something, and then I don't know I couldn't find what the P stands for. And then it actually turns out to be a Koblitz curve, and it's very similar to another curve called R1, so they called it K1, and it has it has P and G and N of length 256 bits. So that breaks apart just about the entire title. Yeah. This stuff? Of course. We can compute it from the signature itself. Exactly. And in fact, we'll see an example of it in the next section. But yeah, your understanding is correct. So both Bitcoin and Ethereum use a curve called SEC 256K1, which which is a curve with the following domain parameters. This is not an NSA curve. There's two big groups of curves. There's the NSA ones, and then there's the SECG ones by the working group called secure encryption, whatever. So this is from the second family. So actually, it turns out that Koblitz curves were not popular at all before Bitcoin. In particular, this one wasn't. but Bitcoin made these curves very popular, and now they're implemented in most crypto libraries because they don't contain the backdoors, or it's very, very unlikely. In fact, there is even a working group on the internet called, I have some resources on this as well, it's quite interesting. Oh yeah. So here's just the quote: "Safe curves, which is a working group to test the whether curves have backdoors, to test the trustworthiness of curves, argues that attackers might have manipulated the choices of standard curves to be vulnerable to a secret attack that applies to a small fraction of curves." Blah blah blah. The curve SEC256K1 is defined by safe curves as a somewhat rigid curve, where the generation process of the curve is generally considered secure. And even the director of this organization went on bitcointalk.org and he confirmed to everyone that he believes it's secure. So which curve are we talking about? We're talking about the curve with the following domain parameters. So P is probably the largest 256-bit prime. What do you think? I'm not sure there's any prime that's bigger than this, or is this an E? Looks like it's an E. A is 0, B is 7, y squared is equal to x cubed plus 7. Generator, which should be which should be point, so it should actually have an x coordinate and a y coordinate. But for example, in Bitcoin we can compress it, and in Ethereum as well. So this is in its compressed form with just the x coordinate, and then the one bit that determines which of the 2 points it is, and the order of the group, which is conveniently smaller than P, but it's smaller only by an extremely small amount. So if you compare this number with this number, they're only about 2 to the minus 128% different. Right? They're very, very similar numbers. This is essentially 2 to the 256, and this is essentially 2 to the 256 minus, let's shave this part off, so this is approximately 2 to the 128. If you compare 2 to the 256 and 2 to the 256 minus 128, they're almost the same. And that's exactly what Haas's theorem would have predicted. As we saw before, P was 17 and was 19, very similar numbers. Here, very similar numbers as well. And finally, the cofactor is 1. That's a very good question. So these are pretty much chosen. I mean, P is pretty much deterministic because, yeah, I believe it's the largest 256-bit prime. And this one, there was some talk that it's not transparent how it was chosen. But I don't know much more about that. Yeah, and then N follows from G. I don't know. So now that's a very good question. I wouldn't know the answer. So now let's have a look at elliptic cryptography in Ethereum. Yeah. So Ethereum transactions have a number of parameters. They have a variable called nonce. They have a variable called gas price, variable called gas or start gas. They have a variable called to and value, which is how much ether you're transferring. Yeah, so I think it's pretty clear. Nonce is how many transactions that account has done. Gas price is how much ether you're willing to pay for one gas. So this guy is willing to pay 20 billion way for one gas. This is how much gas you're sending with the transaction. This is where you're sending the transaction to, either an address or a contract. And this is how much ether you're sending along. And if you're sending it to a contract, it might be useful to provide some data, which in this case is none, because we're transferring ether to, it looks like, a personal account. Well, it doesn't have to be, but you get the idea. This is an Ethereum transaction. So what do we do with an Ethereum transaction? We RLP encode it, just a super fancy way of doing something that's pretty simple, which is turning 9 to hex, 09, turning 20 billion to hex. I'll just show it on one example so I don't bother you. Turning start gas to hex, that would probably be this. Actually, that would probably be this. Turning to address to hex, well, it already is in hex, so that's pretty easy. Turning 10 to the 18 to hex, that's going to be somewhere here. And finally, yeah, this is where it ends up. So 10 to the 18 would actually be somewhere around here or here is my expectation. And what we do once we turn everything to hex is we RLP encode it, so that's why there's an 82 here, that's why there's an EC here, and etc. It just allows us to turn any object using a process called serialization to a number of ones and zeros. Right, so it's just a specific encoding process that Ethereum uses. But it's not that hard. Like, this tells us how many bytes the whole object will have, and then we RLP code each of these objects separately, and the first byte always tells us its length. So 85 will mean that it will have a length of 85. Yeah, a length of 85, and then we actually do the object. Sometimes you have to add a 0 if it is not a perfect number of bytes, such as we have to do with 9 as well. Now, what do we do once we've RLP coded the transaction? We sign it. So here we obtain, so what do we do when we're signing? We randomly generate a K. We multiply the generator by K. We take the X coordinate of that. And for S, that's going to be this. And for S, we compute the inverse of K. And we multiply that with the message hash plus our private key times this. And we do that all mod whatever, and we obtain this. Now, once we have RNS, that's essentially the signature. But Ethereum uses public key recovery, so we don't have to sort through up to 4 different public keys. And also in Ethereum, to prevent replay attacks, so to tell us which chain we're actually on, we add another byte, and we call it V. And that tells us which chain we're on to prevent replay attacks, such as Ethereum, Ethereum Classic, Morden, Robston, Rinkeby, Coven, Gorley, etc., all the different test nets and mainnets for Ethereum. And it also tells us which of the 4 public keys this will correspond to. This together is going to be called a signature, and finally we send across the wire the signed transaction, which is going to be composed of this what we saw previously, the signing data, together with the signature. Okay. And maybe just two very quick points. Number one is we also add VRNS here, but we assume it's 1, 0, and 0 for the process of signing. And then the point number 2 was we don't actually sign this. We sign the hash of this. Why is that? It's exactly what we saw in the deep down theory a few minutes ago, or half an hour ago. If you just take the message without hashing it first, it breaks the security of the system. So that's on the network level. On the EVM level, we have an opcode called EC recover. It takes the hash of the message, the 3 variables used in Ethereum for signatures, and it outputs the public key. Note that it is not taking a message and then hashing it. It is merely using the hash. So the hashing must be done in Solidity or on the EVM before this opcode is called. Otherwise, as we saw, it breaks the security of the system. How much does this opcode cost? It's actually not an opcode. It's a precompiled contract. So you got to call it with 700 gas, and then it costs 3,000 gas to execute. So it's quite expensive. It costs almost 4,000 gas to do public key recovery on Ethereum. What's up?
For the previous slide, when you said that you send it, that it's being sent over the wire, that means from one node to the other node, or what's that?
Yeah, exactly. Yeah. And the only thing I'm not sure about, this is very hard to find, is how Ethereum actually stores the transactions, like in the client, for example, in Geth. But I believe that they also store it in this way. Yeah. So this is essentially just a quick recap of what this is. This is the RMP encoded transaction, the data about the transaction, together with the signature of the hash of the transaction. So this is the actual transaction together with the signature, and what then constitutes the transaction hash? It's merely the hash of this. Yeah, so when you send the transaction in MetaMask, and it shows you, here's your transaction ID, and you look it up on Etherscan, the hash is equal to the hash of this number. So this is the actual transaction, the information and the signature, and the hash of it is the hash of the transaction. And some future developments. So I think Bitcoin is fiddling with this thing called Schnorr signatures, which still using the same curve, just using different algorithm than ECDSA, i.e. one called Schnorr, and that would allow Bitcoin users to sign multiple transactions with one transaction. And Ethereum is fiddling with this thing called account abstraction, which moves the entire elliptic curve / digital signature layer to the EVM, which means that you will be able to do any sort of crypto in the EVM. So you will not be restricted to elliptic curve cryptography, and you will be able to use custom crypto to verify your transactions. So that's pretty cool. And did I want to say another thing? Yeah, that's actually it. Cool, so that's the end. Thank you very much. Do you guys have any questions? Oh. Which one? Okay. Right. Wait, what's the question? I don't understand. Are you talking about the advantages of using count abstraction, so moving the cryptography, the authentication layer to the EVM? What's the advantages of doing that? What? String comparisons? What's the question? When you compare big strings?
Big strings in Solidity, right? Like large strings.
Okay.
You hash them first,
Right.
and then compare the hashes.
Right.
The question is, why do we do that? I don't think it relates to.
Okay, so you have basically two options on the EVM natively implemented for hashing. One of them is KECAC 256, and the other one is SHA-256, SHA-256. KECAC-256 is an opcode. SHA-256 is a precompile. It could be the other way around, but they're very cheap. I think they both cost only about 30 gas plus 6 gas for each word, rounded up. So compared to EC Recover, hash functions are very, very cheap. That's why in one Ethereum transaction, we have like 3 hashings, because you're going to be, to get the hash, you're going to be hashing this, and this itself is, there's maybe more hashings that I forgot, actually. Yeah. In fact, I could get the exact, I have it in my, okay, so I thought I had it. Oh, I do. Let me just check that what I said was correct. I have it right over here. Right. Okay, so there's only 2 hashings. So to get the transaction ID, you hash this, and this itself is, well, part of it is a signature that is a signature on the hash of the actual signing data. So that's why for any Ethereum transaction, there's actually 2 hashings going on just to get the transaction ID. Hashing is very cheap. Any other questions? Okay, cool. So in that case, yeah, go on.
I don't know if I'm the only one over here, but I really did not get it that much with the requirements to provide also the message aside the hash of the message in order, not to break the
security.
break the security.
Right.
So can you just say it in some other words so lazy people would get that without mathematical symbols? LFI.
I don't think I can. So there was a very good discussion. Here, let me show you. So if you go to the tweet, then there's a very good discussion around that. So that might be a good place to start. For example, when I was talking about there's a script that allows anyone to prove that they're Satoshi, this is it. So if you click on this link, you will enter a Python script, which if you will run, you will be able to generate a signature that corresponds to the Bitcoin Genesis public key. Yeah, so this is a script that naively proves that you are Satoshi. Of course, it doesn't, because you are not hashing the message, or alternatively, you are not providing the pre-image of the hash of the message. That's a good question. So the thing is, you can't pick the message using this attack. The message gets calculated deterministically from the numbers of A and B that you pick. So here they pick random numbers A and B, and then the message is calculated deterministically from that.
So the proof was that actually they took some other message, create and assign a message and showing this result has a signature which is relevant or corresponding to the signature of the first transaction.
Exactly.
So it was not like a direct comparison where you would say, okay, here we have derived public, or it was derived public key. That was the point. They were able to derive the public key from something else, showing that this is the public key corresponding to the public key which was used for the first transaction.
I would say it like this. It allows us to generate a signature that corresponds to a specific public key without using the private key. It allows us to generate a signature that corresponds to any public key without using the private key.
And by signature you essentially mean a public key.
No, by signature I mean a signature. Adam? Maybe you can explain it better.
If I got it right, I think like Dominic said that there's a technique to generate a valid signature, basically, but like efficiently, just from public key, right? But there's no technique to generate a valid signature of a hash that you know the original data for, right? So you can generate, if you don't care what you are signing, right? You can generate an arbitrary number of valid signatures, right? But because you have to sign a hash for which you know the data that generated the hash, you can do it, right? So the requirement is not to prove that you have signed something. It's not to just like provide a signature, but also provide a data that generated a hash that was signed, right? And if you have all of this information, you actually, that's the like valid proof that you have actually like properly signed something, right? Is that it?
That's exactly correct. Cool. So thanks a lot for coming, and I'll see you next time.